Hello everyone, here we are again looking at another example of relative motion, a particular example of two-dimensional motion. This one's about a plane trying to go from Houston to Omaha in the northward direction, and it has a particular velocity of 960 kilometers per hour relative to the air. The distance it needs to go between the two cities is 1,290 kilometers. At its cruising altitude, there's a wind blowing in the eastward direction that has a magnitude of 190 kilometers per hour. What we want to figure out is in what direction should the plane fly in order to end up going directly north, and how long will the trip take. So give a shot at writing down an expression that shows how the vectors involved in this problem relate to one another. Pause the video for a second and write down that relationship. And as you're doing it, also think about making a graphical sketch of how those vectors are related. And then when you're done, take off the pause button and we can compare our results. So here's how we can indicate how these vectors are related to one another. We see that we have the idea of these three vectors adding. So the velocity of the plane with respect to the ground is the vector sum of the velocity of the plane with respect to the air and the velocity of the air with respect to the ground. That's the wind. So we've got this represented here as a picture. We've got tail to head gives us the sum, and here's our equation. The next step is to write this equation in terms of x and y components. Pause the video and come on back when you're ready to compare. Okay, let's take a look at what we get considering the sum of the vectors in terms of their components. So for the x component, we have, using this equation here, VPG in the x component is 0, VPA in the x component is VPA times the sine of theta. Theta is this angle here, as I've written it. And if you think about the sine being the opposite over the hypotenuse, you can see how we want the sine component there. And finally, in the x component is the magnitude of the velocity of the wind, the air with respect to the ground. In the y direction, VPG in the y direction is just its magnitude. VPA in the y direction is this component, and that's the adjacent to the angle, so that's going to be VPA times the cosine. And then finally, the component of the velocity that represents the wind, the air with respect to ground, has no component in the y direction. It's all in the x direction. So these are our two equations that we get from considering the components of the vector equation we had before. So now pause the video and solve for theta. What direction should the plane fly? And then come on back and check. To get the direction the plane should fly, we can use the x component equation. And that's what I've done here. I've taken this x component equation and solved for theta. Sine of theta is going to be the ratio of these two velocities. The units cancel. And when you plug it into your calculator to get the inverse sine, you get 11.4 degrees. So the final question is, how long will the trip take? And so have a go at that question and check on back when you're ready. Well, the time of the trip is just going to be the time related to the velocity going a certain distance. So the velocity of the plane with respect to the ground is equal to the distance it travels over the time it takes. And so we can use the y equation here to calculate what the time is. So we swap the place here and solve for time, and we get down here to time. Distance over this velocity VPG, but that's up here, so we're going to plug that in here. And I'm going to enter in the numbers here from the problem. The distance is 1,290 kilometers, and the speed of the plane with respect to air is 960 kilometers per hour. I notice I got a mistake here. This is per hour. And that's also divided by the cosine of theta, which is 11.4 degrees. If you plug all this into your calculator, you come up with an answer of 1.3 hours. That kind of makes sense in the grand scheme of things.